Okay, well, so I think we can start. First of all, welcome everybody. I say good morning to everybody, but I know that are people connected from all over the world, so there may be people from that are attending the meeting at night or in the late afternoon. Thanks for being here. This is, I mean, quite an important event for our group because this is the first time that we disclose some more live information about our library LifeX that we have been developing in the IR group. So since I know that many of the participants have not attended my talk yesterday or are not attending the conference at all, I would start by sharing a few slides from my presentation, just to give you an introductory overview and okay, so that we can start from the same starting point. Okay, I'm going to share my screen. Okay, share the whole screen. So if anybody has already seen my talk yesterday, I will say something. I will repeat myself. So, but it will be just for a few minutes. So forgive me for this. Let me come back to a bit of history. First of all, well, I would like to thank all the collaborators in my group and other users and developers of LifeX that have done much of the work that I will be presenting today. So LifeX is a library with a twofold goal. From the one side, we would like to build a whole heart model prototype, so a virtual heartbeat, including all the different physics, electromechanics, mechanics, fluid models, and so on. From the other hand, another task is to build personalized models to answer patient-specific or, in general, clinical questions. Today, we will see some examples concerning the first point. So we will have a simulation of an idealized heart. Our library relies on DL2, which is a element library. It is open source. You can find it on the web. I strongly suggest you to use it because it is very well documented and provides many useful facilities for handling with finite element problems, mesh handling, and linear algebra, and so on. LifeX is written in C++ using C++ 17 standard, and we are moving towards C++20, which has already been has just been released a few weeks ago. So our code base so far is about 90,000 lines of code. We have many authors, and the development is going faster every day, I would say. So the developing community is increasing and is quite active in this sense. So the general structure of LifeX is well, the base of our code is D2 that provides us the finite element discretizations, mesh handling, linear algebra, as I was saying before. On top of this D2 library, but in an independent core, we have implemented our algorithms and utilities, and I will show some of them later. Then the numerical scheme that we use to tackle the different problems, and in particular the physical models that we have implemented using all this structure are those related in particular to the heart physiology, to the cardiac function, but not limited to this only. And historically, sometimes we have provided some feedback to the community with new features or some small improvements depending on the needs that we had while developing. So I just skip this part because it regards the heart function. I think we can skip it for today. I would like to focus on the main features that I would like to underline and to highlight today. The point is that, well, I think this slide is better summarizes why do we need LifeX, which is another finite element library where there are hundreds available on the web already. We have these goals in particular. Concerning the modeling part, we will deal with multi-physics model, multi-scale models, both in time and space, and geometric coupling. So when you have different geometries that share an interface, but not necessarily, we have implemented some numerical scheme for dealing with all of these mathematical complexities, I would say, and numerical complexities. So we have different core models available, such as electrophysiology, mechanics. I will provide some more detail later. And we also have the possibility to couple all of them together, or some of them together, by using arbitrary discretization scheme. So each model can be discretized using different finite elements, different meshes, and different time steps in a partition, staggered way, so to save computational costs, because all the physics involved show very different dynamics, time dynamics or space dynamics. So they need for different mesh or time resolutions. So the coupling scheme bullet point that I listed here concerns these particular numerical techniques for this kind of complex mathematical models. From the user experience side, our aim was to implement something that, despite the mathematical complexity behind all of these models and numerics, would still be user-friendly and developer-friendly, so that other people can exploit this library or eventually contribute depending on their experience. And of course, our, I would say, main focus is computational efficiency, because such problems are very heavy from a computational point of view, and we can not perform any simulation with a code which is computationally inefficient. So the aim of LifeX is somehow to become a standard library when it will be released publicly, open source, for mainly for the whole model prototype that we are developing in the high-art group, but possibly extending these many features to other applications or other models not concerning the specific cardiac function. So let me, okay, I will show you what is the plan that I have thought of for today. First of all, I will give a general code overview. I would like not to go too much technical, because I know some of you are have a different background than programming or scientific computing, and this is not the goal of this workshop. The second point actually will be the most interactive part. I will show you how to run an electromechanic problem on an idealized geometry from scratch. And in particular, this will involve solving different models. So we'll start with a 0D model. We will add increase the complexity by adding new model and to couple all of them together. So the intermediate step would be to run a 3D electrophysiology on these idealized left half geometry. I know this is not really physiological, but think of it as it represented a left ventricle, the mitral valve, and the left atria. So this is a very a toy model for a coarse mesh for running simulations live on even on my laptop. Then we will add also the mechanical part, and we'll conclude with the full electromechanics model. And by the end of this session, of course, I will be open for questions. And please feel free to interrupt me at any moment for any kind of question, curiosity, or anything you would like to comment about what I'm going to present. Okay, so can you see my screen, right? Also the terminal.
Yes, we can see.
Okay, thank you. This is the LifeX directory. There are many files, many subdirectories. Just to give you an introduction on how LifeX is composed, the main directory is called, as you may suppose, is called LifeX, and it contains different folders. There is the computational core that exposes some common facilities that need to be shared among all the physics. In particular, I will show you more details about parameter handling. Is a point that we have put a lot of effort into in the past 2 years. Then we have the physics directory containing the different physical models implementations. So you can see the RC problem, zero-D circulation model, electromechanics, electrophysiology, fluid dynamics, implementing the Navier-Stokes equations, and so on. And finally, we have a utils folder, containing some utility for geometry handling, for dealing with input and output formats, and to implement numerical schemes. In particular, the numerics folders contain some abstract handler that we have implemented to make the implementation of complex problems, such as nonlinear or time-dependent problems, or the combination of both, even in the vectorial case, so the most general partial differential equation that you can ever imagine in a user-friendly way. And all of these codes actually rely on the interface exposed by the DIL2 library, and we have provided some abstraction just for convenience and to have a nicer interface in the context of having multiple models in physics that share a common language, I would say, in the same library. So in particular, we have a linear solver handler, nonlinear solver handler, preconditional handler, boundary condition, time advancing, but we will see some of these tools more in details in a few minutes. Okay, so we have seen the LifeX folder, then we have an apps folder that contains the main applications that the user can run, and we have basically one application for each of the core model that we are able to run, but not only. So we can run electrophysiology as a standalone model, mechanics as a standalone model, we have some facility for input data preprocessing or post-processing, and also a couple problems such as electromechanics, which is the one we are focusing on today. I would like to say that today, for timing reasons, I will not have the opportunity to show all the models available inside LifeX, but there are many of them, many others that have been developed and are at a quite stable development stage, in particular the fluid dynamics, which has very advanced features. Also the coupling of the electrophysiology problem with the torso for ECG reconstruction, for example, and many others. Then going back, we have an example folders containing some applications of these apps that I have just shown you, and then a test folder that just performs basic checks or validates the implemented code against some reference solutions or exact solutions where available. So to make sure that every change that we make to the library is always consistent, backward compatible, and does not break the existing code, I would say. For those of you who are expert in software development, we use CMake as a configuration tool, and everything is, of course, stored on a Git repository that will be publicly released by the end of this year. So let me start by showing you one example, which is actually a tutorial. Let me move here. So the window I'm showing you now is the main web page of the LifeX documentation. It is online, but so far it is restricted to the developer group, but it will be released as well together with the code. And here you can find the instructions on how to download and install LifeX, how to run LifeX applications, and also a set of tutorials, the coding styles and guidelines, which are meant for developers, and links to some of these two tutorials that we find useful for introducing people, students, and general users to the LifeX library. So just I will give you a brief overview of what is contained in these web pages. Is the download and install instructions, where everything is highly detailed. You have many different ways to install dependencies and to compile effects. We are planning also to provide binaries for at least for some Linux system, so that people can just download a code and run it without any compilation phase or other painful things. Here are the instructions on how to run all the LifeX applications, and this page actually is general because all the applications have the same interface, expose the same interface to the user, the same command line. And I will show you what this interface consists of, in particular in terms of controlling tuning the parameters for a given simulation scenario, for a given model. And we also have a set of introductory tutorials that span from solving a simple Laplace equation using our linear solver and boundary condition handler. And these tutorials are of increasing difficulty. So just to give you a very quick idea, let me show you this very simple equation It's a elliptic equation with a nonlinear reaction term and an exact solution, which is given by the exponential of the sum of the three coordinates. So very simple problem. It has been linearized using Newton's method. So we at each time step we solve for the increment delta u, and then we update the solution until convergence. This will be the only source code that I will show you today. So those of you who are not experienced in C++, don't be scared. It is just not to give you many technical details, but only to give you really a high-level overview. So the main points of running this simulation is this one. And I show the most relevant part of code. So running the simulation consists of different steps, such as creating the mesh, or reading it from file, or something like that. So we generate the geometry in which we are running the simulation on. Then we set some boundary conditions. They can be Dirichlet, Neumann, Robin boundary conditions. We have a BC handler that is able to deal with all of these different possible combinations. So to every phase of our domain or interface, more in general, we can impose some, I don't know, analytical function or some other finite element solution as a boundary condition. Then we have two functions. This assembled system actually assembles the finite element discretization for this problem. So it assembles the residual and the Jacobian matrix, which in this case has a diffusion term and a linearized reaction term. So assembled system creates a global matrix and a global vector representing the model that we have we are taking under consideration. And finally, solve system solves the resulting linear system coming from the discretization using finite elements of this problem. And once defined assembled system and solved system, we can just solve our code using nonlinear solver. And the linear solver needs to know how to assemble the problem at every iteration, and how to solve the problem at each nonlinear iteration. So everything is hidden behind this call. The user does not have to implement the Newton method, in this case by itself, and everything is under the hood and ready for using, as you can see, with a very nice interface. And then we output the results. So that's I don't know if you have any questions or curiosities. As I said before, please feel free to interrupt me. Then let me move toward another example, which is tutorial 4, which solves the same equation, but with a derivative in time term, an additional time derivative. So this makes the problem time dependent. I will not show the source code for this, but it is very similar to what we have called nonlinear solver.solve. We have also a time advance handler time advance for abstracting and letting the user unaware of what is going under the hood. And of course, all of these facilities have been tested on different benchmark problems, so the user can rely and can trust the implementation of these low-level solvers and numerical schemes. The reason why I am showing you this example is to motivate one of the main objectives of the LifeX library, which is to expose parameters controlling one simulation in the most convenient way, depending on the user experience. And I think that giving you an example would be much more clear that we can do, that I would say in words. So every application comes with an help, with a brief documentation here, where you can see how to specify different parameters. Possibly this will be generalized into a nicer graphical user interface for those who are not experienced of Linux or terminal or other scripting languages. All the application share these two parameters, which are -g and -f. The purpose of these is shown on the slide. For running the simulation, we need to perform 3 different steps. First of all, we generate a default parameter file or files, depending on the need, containing, we will see it in a while. Then we open this file, we modify it by setting our own geometry, our coefficient, or I don't know, any kind of parameter or coefficient that you can imagine of in a finite element simulation, and then we run the simulation using the parameters set at point 2. So first step is enabled using the -g flag. So if I run this LifeX tutorial 04, the -g flag, well, first of all, let me show you that this folder only contains the executables, which are these files listed in green. If I go with the -g flag, so this run the parameter generation, which is of course very fast, and this populates the folder with one additional file, which is a text file, a parameter file containing the parameters that are exposed to the user. So there's no need to go inside the source code to modify the simulation, but everything is contained in this file. What's the point of this? Of having a more general way to generate parameter files. Well, let me show you directly on this example. There are very simple problems on which there are many parameters to be set, at least in principle. So you have the part concerning the mesh discretization, the time solver, you have nonlinear solver parameters, so residual number of iterations, tolerances, and also for the linear solver used inside the nonlinear solver, you can set the maximum number of iterations, tolerance, solver type, but in most cases, the large part of these parameters can be left unchanged. I mean, the default values that we have set inside the library are good for simulating most of the scenarios that we are targeting. So it is not good to expose all of these very long files to users. We aim at keeping things very simple and user-friendly. So we have thought of a way of letting the user choose what kind of parameters he or she would like to control in these parameter settings. So the -G flag by default generates, well, we have 3 different levels of verbosity. -G is the intermediate one, or we can say -G minimal, that generates the same file, but containing only minimal information required to run a simulation. So the basic information that the user for sure has to provide is, well, something related to the initial mesh. In this case, how many times it is refined with respect to the original imported mesh. And then, I mean, 3 basic parameters are initial time, final time, and the time step. So you can see the complexity of this parameter file is highly reduced in this way. So depending on your experience, you may decide to generate a simple parameter file, so only minimal settings, or the intermediate one that I have shown before. No, actually, I didn't, which is a compromise between the 2 endpoints that I have just shown you. So, for example, here we can also set the finite element space degree, the degree of the polynomial that we are using for discretizing the problem, or the BDF order used for the time discretization and time advancing scheme. So let me show you a comparison so that things actually can be made clear. So I generate 3 different files with the different configurations and open all of them together. So we generate level 0 verbosity, the level 1 verbosity, and level 2 verbosity. Okay, so suppose the parameter file name is arbitrary, I can set whatever desired. So just for comparison, let me do this. Okay. These are the 3 files. We have level 0 here on top left, level 1 on bottom left, and on the right we have level 2. As you can see, they all represent the same simulation, but different parameters are exposed. In the simple case, as I have just shown you, we have the number of refinements, initial time, final time, and time step, and that's all. Everything else is takes a default value. So in principle can be altered by the user, but is not exposed in this interface. The intermediate level of verbosity also contains the FE space degree, which was not in the level 0 file, because we think that this parameter is a bit more advanced, so it can be set by a user that I don't know, has at least some experience in numerical analysis or like that, and the same for the BDF order, which is now here present and was not present in the minimal file. Whereas the full file contains a superset of the others. So we have the same subsections, mesh, time solver with the same parameters and possibly others, but also parameters related to low-level numerical issues, such as nonlinear solver, as I have shown you before. We can control the tolerances, the method to apply, linear solver again, and so on. And for each of these linear solver, we can also set the preconditioning or the GMRS. Of course, we have other parameters to control, and this level 2 parameter file is supposed for experienced users that want to have control on everything that is happening inside the simulation. Also, preconditioners for the linear system and related parameters can be set up. So the syntax for this file comes from these two actually. This is the parameter handler facility in these two, and it is a text file, simple text file that it is very human readable and human modifiable, in my opinion, and everything is documented. And the good thing, another good thing of this file format is that we can control what the user sets. So, for example, if the user by mistake set as FE space degree something like -3, which of course does not make sense, then an exception will be thrown. The user receives an error message, and in the terminal we print, please be careful that FE space degree must be at least a positive and non-negative number. Or if you set the final time, which is smaller than the initial time, the same. Or if you set something that is not available in the library. So here the documentation says that for this problem we can choose between conjugate gradient, GMRS, or BI-CG stub linear solver type. So I can just choose between these three alternatives. If I set another kind of I don't know, custom preload solver, then the program will not run and will say you are setting a wrong parameter. And this is useful for controlling also physically relevant parameters, because there are certain quantities that, such as, I don't know, length or think of the mass of the body. From a physical point of view, it cannot be a negative number. So this parameter handler from these two that we have somehow generalized for adding these new functionalities can specify a range or a type of parameters that can be set. Another example is setting a string Of course, this is not allowed because FE space degree is supposed to be an integer number. So this is convenient and makes the code robust against possible mistakes made by the user. So this is the way we control all parameters in all the different physical models. Of course, the more complex the physical model we want to simulate is, and the more complex the corresponding parameter file is. And this is the reason why we have the possibility of exposing just the minimal set of parameters that need to be controlled, unless the user aims at doing something more advanced. So finally, once we have set all parameters in this file, we can simply run the simulation. This time we do not specify the -g flag. This is only for the generation of parameter files and not for running the actual simulation. And as you can see, the problem starts to be solved. we have the time advancing scheme, some information is printed, we have the Newton iteration, increment. This can be disabled if you don't wish to investigate all of these numerical parameters. And finally, we have a summary of the computational time taken by each part of the simulation. A custom parameter name. So by default, without specifying anything, the parameter file is the one having the same name as the executable. But if I want to use, for example, level2.prm, which I have just generated, it is easy to set with the -f flag. -f stands for file, parameter file name. So in this way, I can save different combinations on my PC for running, I don't know, the same simulation by changing one parameter and make this procedure feasible without compiling or doing more complex stuff. I think that if I run this with level 2, I will get an error. I don't know if I save with a okay. But just to give you a live example on the kind of control that we have here. Let me set, I don't know, a t-space degree equals to -2. And as you can see, the application does not run, and in particular, the error message coming from the dict library is quite expressive in this sense. And it says that the entry value -2 for the parameter at t-space degree does not match the given factor. So we have written in the code that this parameter must be non-negative. So the range, the integer range that this value can take is higher than. I think here's some. Okay. Must be non-negative. So I don't know, is there any question so far or curiosity? Okay, I see a message in the chat. Okay, how you impose the boundary condition? So to answer to this question, I need to show you some source code where we actually impose arbitrary boundary condition, and this is the one I was showing before. So you define a function. Assume, for example, you want to impose Dirichlet boundary. Okay, here it is. So this problem, we have a Dirichlet atom on the whole boundary of the domain. And this means that, well, the domain is a hypercube in 3 dimensions. This means that for every phase in the domain, we need to impose this analytical function . So I will not show you the technical details because it will take too long and will be a bit boring, but the goal is that our BC handler enables to write like, I'm assuming that every phase in the input mesh has a boundary tag, a boundary ID on the different phases, so we can easily recognize different boundaries. So I would say that boundary 0, I don't know, we can impose x plus y function. This is not C++. This will not compile and will not work, but just to show you what happens. We can say that on phase 3 we impose the exponential of x and something like that. And a very similar syntax can be used for imposing normal boundary conditions. So our BC handler, actually, maybe I can show you the documentation, which should be more expressive than. I think that the server of Plotec is well, it doesn't matter. At some point, it will work. We can impose so the declare conditions. We can assemble automatically normal contributions, so boundary integrals to add to the right hand side, and also Robin conditions that additionally build an additional local matrix to be added to the left hand side, so to the system matrix. For vector problems, the decay conditions can be set also on one component. You can set the normal component or the tangential component, so you can specify which component to select. And well, this is the idea behind. More in detail, decay conditions can be imposed in different ways, but the most common thing that we do is to impose them as a linear constraint in the resulting linear system. So we basically eliminate the degrees of freedom associated with decay dots and remove them from the linear system by imposing those constraints on other on the variables depending on these the degrees of freedom, which are located on phase 0 and phase 3. I don't know if this answers the question. In case something is not clear, just please tell me. Then I see that Massimiliano has raised his hand. So please, Massimiliano. Actually,
can you hear me now?
Cannot hear you. Yeah, I can.
Okay, sorry. Yeah, I saw that you saved to XDMF format with creating several files, or as far as I could. So while you could, if you want to append to the same one, is there a reason why you choose to have several files?
Well, actually, we have two main reasons for having different files. One reason is to have simply to have different snapshots of the parameters for a single simulation, to keep them on your computer and possibly reuse them later, one or the other, depending on the simulation you want to rerun, or even to recall which parameters were used for some simulation results that you have run, I don't know, months ago, and you don't even remember what was the parameter setup. But the most important reason is that is due to the fact that we are dealing with complex problems, such as if you take, for example, the electrophysiology. Sorry, let me. I'm not in the directory. So if I run the -g, if I generate parameter file for the electrophysiology app, sorry, I'm in the wrong folder, so I cannot show you what I was meaning to. You see that in this case, different default parameters files are generated. This is because, well, there are some parameters that are in common among the different physical models, but complex physical models, as you know, can have some difference. You have some model tuning. In particular, I don't know if you are familiar with electrophysiology, but we have implemented in LifeX both the monodomain and the bidomain equation. And in this case, we can automatically provide the user a set of default parameters for the monodomain problem or for the bidomain problem. So if one is interested into running the monodomain problem, then this will be the parameter file used. Otherwise, the other one. And of course, starting from these two, the user can customize them and possibly write his or her own parameters.
Excuse me. I was maybe I phrased it poorly. I was thinking of the solution files when you already run a test simulation.
Okay.
And then in the listing of the folder, I think I saw several solution this, solution that files.
Oh, you mean these files?
Yes, those files.
Oh, sorry, I didn't get the question actually. So
no problem.
Sorry.
Those could be appended into one.
Well, actually, in principle they could, but the advantage of this is that we can save the mesh only at the first time step if the mesh does not change in time.
Yes.
And all other files contain pointers to the mesh contained in the initial file.
Yes.
So in principle there is no, well, in principle yes, you could write everything in the same file, but when you are transferring files from an HPC facilities to your laptop, it is more convenient to have separate files.
Yeah, that is true. That is true. Especially if you want to just visualize like one of them.
Yeah, exactly. Or if you want to visualize a partial solution while the simulation is still running, this method is more robust, in my opinion.
Okay. Yeah. Thank you.
Thank you. You're welcome. Okay. Are there any other questions? Okay. Okay, I see a question by Professor Wittmann. So please unmute yourself.
Hi. So yeah, a couple questions. You said you're moving to C, let's see, 20? C++ 20?
Yeah.
I don't know. Do you foresee problems with that? Because I know with a lot of installations, even though it seems like it should be up to date, there's always issues with compilers. People have old versions of OSs like Ubuntu 16, and sometimes C20 might not always be available or fully operational.
Okay, well, to answer to this question, I would say that our philosophy since the beginning of the LifeX development, we have always tried to use the most recent, most up-to-date versions of all of our dependencies. This has many different reasons. And in my opinion and in my small experience, usually new versions are, well, this is not always true, but sometimes, most of the times they are improvements of previous versions. So we try to keep all of our dependencies, in particular the compiler, of course, the or I can hear an echo, sorry. So VTK, which is another dependency, up to date with the latest version. Of course, this requires us to readapt our code to the new versions, but I think that in the long run, this strategy will be good. And concerning the point that, well, you may say that different HPC facilities, for example, do not have a recent compiler for C++20. We also provide instructions for compiling the new compiler using a previous version of the compiler. So in the end, you end up with the same minimum version number of the requirements of LifeX.
No, I mean, I agree that the new versions are always better for the developers to make things better. And new versions, they probably fix old bugs and they always reintroduce and they introduce settler new bugs, but generally things improve. So yeah, it's just that in my experience, it can be problematic.
Yeah.
Yeah, so actually, so what is the underlying framework for your multiprocessor computation?
Okay, we all the code base in LifeX is parallel. We rely on NTI, OpenMTI in particular, but it works also with. I think we have tried with the Intel implementation of NTI, and it has been run on different HPC facilities. Yesterday, I have been showing this. Spelling test. So I don't know, maybe I didn't get very well the question. So what do you mean? How do we handle with multiprocessor? Sorry, we cannot hear you. You have your microphone muted.
Oh, sorry. So are you just using plain MPI, or are you not building any other, like using PETC on top of it or anything, or OpenCL? You're just plain MPI?
A combination of both. Thanks to these two library, we have 3 different backends that we may choose among for linear algebra. So we can use either PETC or Tridinos, or the D2 implementation of linear algebra, so distributed vectors, matrices, and solvers. But also, in some part of our algorithms, we also use MPI. And this is particularly useful for interface problems, where you have 2 independent meshes like this, and there is no guarantee that the partitioning is consistent among the different processors. And in this case, we need to locate which processor owns which DOF, and then to share the interface numbering among the processors that are involved. And in that case, we use lower level MPI functions. But in that case, I don't think, I don't know, I'm not aware of better or less painful solutions.
Yeah, I think, I mean, yeah, I'm familiar with these issues, and probably there's a PETC index mapper, but again, you have to set it up which uses MPI. Anyways, I know how much work setting up a piece of code like this, especially complicated, and so yeah, I think it's encouraging and looks like a nice piece. That's all my questions. Thanks.
Sorry, I couldn't hear you for a few seconds.
Sorry, yeah, no, sorry, I'm on my phone. Yeah, no, I know how complicated it is setting up these complex simulations, and I was just gonna say that's a nice piece of work you presented. Yeah, I think I don't have any more questions. Did you hear that?
Oh, sorry. I think I don't know if it is my connection problem. Did you ask how long this?
No. There's no problem on your end. It's my end. So I have no more questions.
Okay. So thank you. Okay. Other questions from the audience? Okay, so I think we can start to have a look at the real aim of this workshop, which is how to run electromechanics simulations. A disclaimer, this geometry is highly idealized. As you can see, this is not really similar to a human heart. So the results will not be physiological in terms of human physiology. But this is just a proof of concept on how our code works. And actually, we have extended this pipeline also to more complex geometries, as shown in some slides, some other slides in my presentation, such as this is for the fluid dynamics or electromechanics on the whole mesh to get more realistic or even patient-specific simulations. So let's start with the zero-D electrophysiology. Zero-D electrophysiology actually means modeling ionic channels. So the ionic passage from the outside of the myocardial cell membrane to the inside, and vice versa in the different phases of the heartbeat. We have different ionic species such as calcium, potassium, sodium, and so on that are involved in this phenomenon. And there are many physical-based or actually, I think most of them are evidence-based phenomenological models for describing these dynamics on different types of myocardial cells, depending on where they are. And these are all the ionic models that we have implemented in LifeX. They can be either run in a zero-D simulation, so to reproduce just an action potential like this, or coupled with a three-dimensional simulation, where they are solved at every degree of freedom to provide a three-dimensional feedback to the electrophysiology problem. Okay. Okay, so let's start with this point, zero-D electrophysiology. In LifeX, actually, just as a naming convention, we have called this application ionic zero-D. So again, I'm in the wrong folder. Sorry about going live with these things, of course, makes things a bit longer. So I generate the full parameter file for this application. We have, first of all, basic parameters, which tells us which model to choose. Oh, well, actually, sorry, before showing you the code and the user, for those who are not in the electrophysiology context, an ionic model is a set of partial differential, ordinary differential equations of this kind, where you have U, that is the transmembrane potential, the real solution of the electrophysiology problems, and W are ionic or gating variables representing the concentration of calcium, sodium, and so on. And depending on the model, this function G can take different expressions, analytical expressions. So switching from one model to the other, of course, it depends on what kind of simulation we are running. There are models with very few unknowns, such as Pamphilo, which has only one gating variable, so this equation is scalar. And we have more complex models, such as the Tentascher-Pamphilo or the Thorold model, also the O'Hara-Rudy, that have tens of these ordinary differential equations to be solved. Well, the first parameter that we expose to the user is how, which kind of model to enable. We can select, I don't know, the Bueno or audio model. If you're interested, I can provide all the references to the paper where these models were presented. We can have different combinations for the parameters, the coefficient of this model. Well, this is the full parameter file, so there will be a lot of useless parameters for this specific simulation. And then for all ionic model, you have the physical constants that can be set from the parameter file. So an envelope is 6 coefficients. We use a nonlinear solver for solving that ODE, and we can set the maximum number of iterations and the tolerance as a stopping criterion. Time solver is something which is in common with all the ionic models. Again, you can set the initial time, the final time of the simulation, and the discretization order and the time step, and so on. And the same holds also for all other ionic models. So BTS, Buenrobio, which with its own physical constants, and so on. CRN, and well, you see this file is quite long because it contains many parameters, and I run the minimal version of the parameter file. It will be much more readable, I guess. Okay, well, it is more self-contained now. We can just set the ionic model with the false coefficients that are coded inside LifeX. So let me set again Buenrobio. We can set an applied stimulus for the 0D simulation. We can set the time where the stimulus is applied, its duration, and its impulse amplitude. And we can, well, the output will be saved in a CSV file for post-processing or for just for visualization reasons. So now I can just run the app. You see, the 0D simulation is quite fast because well, there's nothing really heavy from a computational point of view. And well, actually, most of the time was spent in writing the CSV file. So you see that the computational is very fast, even taking 10,000 of time steps. And we find the solution in this file, ionic model 0d.csv. This file name can be customized. So you have a file name where the first column represents time. So, let me see if okay. Well, represents time. The second, the transmembrane potential by solving the 0D monodomain equation. The calcium concentration, which is the most relevant ionic species used for other mechanical problems and electromechanical coupling. And the three gating variables that in which the Buenrobio model consists of. So we can take this CSV, we can plot it, for example, using any kind of scripting language or visualization tool. I have here some example of simulations generated like this. This is the output of the Buenrobio model with this specific set of parameters. So we can simulate the action potential. This is the concentration of calcium. And the third plot actually shows the dynamics of the three W0, W1, and W2 variables. So first step, so running a 0D simulation, a cell level simulation is quite easy. You just need to select the model and to plot the results. Any question on this part? Okay. So we have now we are done with the ionic 0D model, and now the second part is to take a three-dimensional geometry, which is this acorn geometry that I explained you before, and to generate the so-called myocardial fibers. Again, for those who are not in the cardiac simulation, cardiac modeling field, what are cardiac fibers? Well, basically they are the direction of muscular fibers that compose the myocardial tissue. And from a modeling perspective, they are used to model the conductivity tensor for the monodomain equation. In particular, well, I don't give you all the details of this formulation because it is quite known in the literature. But the diffusion tensor, sigma m, is given in terms of these vector fields F0 and 0 and S0 that are three vectors. They form an orthonormal basis at each degree of freedom. So before running the real monodomain or bidomain problem, we need to generate these fibers. And for this, we have a dedicated application which is called fiber generation. Let me show you the parameters. Generate again a set of parameters. But by default, we can only control the output. But for example, the second level of verbosity exposes again the space degree for computing these Laplacian solutions that are used with some post-processing to generate the fiber field, the mesh on which we want to apply the fiber generation, possibly scaling factors and number of refinements. And for every type of cardiac chamber, we have different algorithms that were presented in this paper. Okay, in this reference, you can find all the details about the numerical methods for generate fibers and to use them in an electrophysiology context. We may even import fibers from file if they were already generated by another tool or in a pre-processing phase. And for each kind of chamber, so we have the whole heart, the idealized heart, or left ventricle, the two ventricles, or for atria also. We can set, so going, for example, to left ventricle, we can set, first of all, the boundary IDs of the different part of the domain. So the epicardium, the endocardium, and if we have just a ventricle, the base of the ventricle. We have different algorithms to run this fiber generation. We control the angle of the rotation of the fibers and so on. I will just show you the result because it will be much more expressive than what I can tell in words. So the fiber generation, again, is quite a fast procedure. It exports this HTML file that we can visualize using, for example, Paraview or Visit or other software for visualization purposes. So I show you an example on an idealized left ventricle, so which is an ellipsoid, a cut ellipsoid, and we can visualize the three fiber fields that are F0 and 0 and S0. Okay, let's not rescale anything. And let me make these a bit more transparent so you can see what's going on inside the domain. So, for example, F0 is this vector field. So at every computational, every degree of freedom, in this case, since they are P1 elements, they are located at cell vertices. You have a vector describing the direction. And this is used to model the conduction. Well, this is used in many different models for the cardiac function, but in particular, this tells the direction, the preferential direction where the electric signal propagates. And well, these rules were determined using experimental data. They are tuned on realistic patients, so they are trustable sources of the fiber orientation. And also here at the apex, you see that we can get a nice proper physiological, even if we are dealing with an idealized geometry. I just show very quickly a brief example of the exact same thing, but on a more realistic left ventricle, which is a left ventricle provided by the zygote company that sells CAD models for the whole body, actually. Okay. And plot F0. Now, this mesh is a bit finer, so the result is more accurate, naturally. Or we may plot N0, which is these other field here, or S0, which is orthonormal at every degree of freedom to the other two vectors. So in this case, it points from the endocardium to the epicardium, and if seen from top, you can see some rotations on the angle of this field. It is not simply normal to the surface. And well, we can save time, and I can just show you that on the idealized left half geometry, this is what we get, with a much nicer representation that was done by Roberto, one of my colleagues. Okay. So now, we are now at the point on being able to run three-dimensional electrophysiology simulations. So the problem that we would like to solve. So in this formulation, please neglect all the colored terms. So we have basically a time derivative of the transmembrane potential U. We have a diffusion term with the diffusion tensor depending on these fiber fields that I have just shown you. Is a linear term. Then we have two nonlinear, highly nonlinear reaction terms, and an external applied stimulus. So there are different steps to take into account to reach to a final monodomain simulation, or by domain, which is well, I can just show you the equations. They are just a bit more complicated, but the model, the underlying model, derives from the same physical evidence. Okay. Also, for the electrophysiology as a standalone, we have a separate application. Let me show you the minimal set of parameters. I'll generate all of them. So we can convert them later. Okay. Here we can set again the mesh on which we want to run the simulation, scaling factor, requirements, polynomial degree. Some of us are working on high order spectral methods, spectral element methods for cardiac electrophysiology. This is an ongoing work. So we may use space degree up to 4, 5, 6 in order to improve the accuracy. Here we can specify which models to run, and the possibilities are monodomain, pseudo bidomain, or bidomain. We also have the aconal model, which is available as a different application because the implementation is different, since the nature of the model is not the same. Well, interpolation method is a technical parameter relating on how these terms are linearized and discretized in particular. Then we can set all the parameters, these key, CM, and so on. And finally, we can set the monodomain conductivities, which are these sigma m transversal, sigma m longitudinal, and sigma m normal, which are the conductivities along the free fields, so respectively along F0, along S0, if I'm not wrong, and along N0. So on each of these directions, we can specify different conductivities, and this comes from physical evidence. There are preferential directions which the electric signal propagates. Then we time solver again. I just keep parts that are not relevant for this workshop today. Time solver output, and in this section we can set the form of the applied stimulus. Of course, depending on the application, these applied stimulus can have different forms. Usually, for I don't know, idealized or simple realistic simulations, it is given as some, I don't know, Gaussian centered at a specific point of the domain, or more points of the domain, which acts only for a specific time interval. And this section enables us to do this. So, for example, we can set a Gaussian type of impulse. So we set the coordinates of the point or points, multiple points where we want to apply this stimulus. We can set the amplitudes, so the intensity of the applied stimulus, how this Gaussian is extended into neighbor cells, and finally the initial time of the applied stimulus. And then again, we can control fiber generation parameters. Going more to the second level of verbosity, here you see that. Sorry. Okay, here they are. I didn't show you before, but of course, even in a three-dimensional simulation, we can choose which ionic model to run. Pamphilo, Ponerovio, Tentasher, and so on. So we can take these parameters, we run a standard simulation. Let me redirect the output to a specific folder, and it runs. It starts the time loop with the specified time step, which is 10 to the -4 in this case. We have set the Tentasher Pamphilo 06 ionic model, and it prints the linear solver iterations performed at each step. And well, we can let it go until it reaches the whole heartbeat, but in this case you find it a bit slow because it is being run in serial. As I was mentioning before, it can be run in parallel. On this virtual environment, I only have 4 processors available, but we have tested it up to thousands, of course, and this should speed up the simulation. The speed up for the electrophysiology model is particularly good compared to the other. So while the simulation is running, I'll just show you again the picture. So for a large problem, we got a speed up to 2,000 cores. We didn't go beyond this limit due to HPC facility restrictions, but well, the speed up is quite the ideal one, which is a very satisfying result. Okay, while it is going, it prints the iterations. Let me just stop the simulation, and I'll show you which kind of solution we can get. Okay, so well, this is again only the left ventricle, but in the end we will see the full left heart idealized geometry. So we will touch also atria. And as an output here we have the transmembrane potential U and the calcium concentration in every degree of freedom of the computational mesh. So just to show you. Okay, the transmembrane potential. You can see that there is a propagating wavefront. The whole domain first depolarizes and then repolarizes again. And the calcium dynamics that drives this phenomenon is quite similar. But well, the scale is different, so we are not seeing that much. So let me restart the video again. So the calcium dynamics is very similar, and this is the solution to one of the solutions to the ionic model. And this actually is obtained using a very accurate ionic model, which is the Tentasher Pamphilo. And you see that on a coarse mesh, the simulation is it is quite fast. We can do a think and heartbeat in just a very few minutes. Okay, I think that if you are okay, we can take like a 15-minute break now, and then we can start again with the second part, where we will see how to integrate mechanics and electromechanics in this simulation. What do you think? Is that fine?
Can I ask a quick question?
Oh, yes, please.
Can you show the scalability results again, please?
Here?
No, the speed up.
Oh, yeah, sorry. Speed up.
This is for quadrilateral elements, is that correct?
It is correct.
Do you get similar speed up for tetras?
Well, this is quite a delicate point. In principle, I would say yes. I know that there are some of these two authors online on this room now, and I need to tell you that before we starting to use these two, only hexahedral meshes were supported, but in the last year they have put a lot of effort into bringing support to tetrahedra without going too invasively inside the code or to modify the user interface exposed by the triangulation class of these two. Indeed, one of the we have not done yet, but it is in my in my to-do list for the next month to upgrade not only the compiler to a C++20 compliant compiler, but also to update these two versions that we have used so far, version 9.2, but being just released a few weeks ago, version 9.3, which brings support to tetrahedra. This will be a great addition also to our software, and well, I will let you know if we have the same kind of speed up. But I know the developing the two developer team very well, so I think they have done a good job in this sense.
Good, thank you.
Thank you. Okay. So if there is no other question, I think that we can start again in like, yeah, well, 15 minutes. So let's take a short break before going on. Okay, I think it's time to start with the second part of this workshop. I'm going to share my screen. Okay, here we are. Okay, so we left before the break with an electrophysiology simulation on this course mesh. Well, actually, in my presentation, I promised you to show one example of multi-chamber electrophysiology simulation. So coupling the idealized left ventricle with an idealized atrium with a connected mitral valve, which is from physiological evidence, a non-conductive tissue. So the two regions are isolated. With the same application that, the same application that I have just used to run the electrophysiology simulation, we have one additional parameter where we may specify a list of volume names. In this case, there will be three. In particular, we will have the left ventricle, the mitral valve, and the left atrium. We divide the mesh in three parts because in each of the three parts we would like to okay. You have a very example simulation. In each of the three parts, we would like to set different coefficients. I mean, the model is the same, but the dynamics of ionic channels in the atria is different from those in the ventricle. So we would likely choose a different ionic model for the two chambers, and we would like to disable the ionic part, so the conduction in the mitral valve. So in principle, we could, well, we actually solve the same system, but the coefficients need to be assembled in different ways depending on the portion of the domain that we are focusing on. And the main point is that the input mesh must provide volumetric tags so that we can distinguish among the different regions. So assume that the ventricle is region 10, the mitral valve is region 20, and left atrium is region 30, just to say. So we can specify one additional parameter that is the volume names. So here I can, while generating the parameter file, so using the -g flag, we can specify as many volumes as we desire. So I don't know, you may write all heart, and it will just generate one parameter section. Or we may specify, like in this case, left ventricle, mitral valve, annulus, and left atrium. The names are arbitrary. You may choose whatever name you desire. So this syntax tells the application that we have. It needs to consider 3 different volumes and the specific model parameters that are chamber dependent, so that may change in different points of the domain, needs to be repeated 3 different times. One for the ventricle, one for the valve, and one for the atrium. What do we get in this case is that you see we have a subsection left ventricle where we can set the volume identifier for that specific chamber, like, I don't know, 10, this depends on your mesh codes generated, and we can set a ionic model, like tensile functional in this case, which is tuned for ventricle simulations. Then we go down and we have exactly the same subsection, but for the mitral valve annulus. Here we can set the material IDs, which can be, I don't know, 20, depending on your input mesh. We have also this parameter where we can set to disable electrical conduction on a specific volume, which is insulator, basically. And in this case, the mitral valve is insulating. And in this case, the ionic model and the conductivities are neglected. So nothing is assembled or solved in the mitral valve annulus, while it is still present in the input mesh. And the same for the left atrium, where we set its volumetric ID, and we set another ionic model, such as the Kurtemanche Ramirez Knaptel, which is tuned for atria. And each of these subsections also has its own conductivities and all other parameters related to these different models. We are seeing that things are becoming a bit complicated. So reading or editing a very long parameter file like this can be not very friendly from the user perspective. So something that I didn't mention to you is that we can deal with parameter files written in different formats. In particular, the same parameter, well, this is the PRM format, which is the syntax, subsection, set, and end for the parameters. This is not a common format. It has been decided by the DIL2 community. But along with this file format, we can input parameter files written in XML or even in JSON file format. So I may tell the application to generate the same parameter file in XML format. I forgot it myself. And it creates this LifeX XML, and the same in JSON format. Why do we provide this redundancy in the code? Because depending on how you are going to process the parameter file, you may find useful interfaces for processing more standard, more common data formats such as JSON or XML. In particular, I would show you here an example on using a graphical interface for setting the parameters using the XML file. And here I have generated as usual, the minimal set of parameters, the full set of parameters, and the intermediate one. So what happens in this case? Well, you have this very nice graphical interface, but I think you may find also different interfaces for XML and JSON formats. And you see a folder structure that replicates the structure of the parameter in which parameters are defined. So you can unfold the mesh and space discretization, and you here may set a different mesh, you set other parameters, and here below you find the parameter documentation, so you always know which value and what this parameter is referring to. And the good thing is that for selections, for selective parameters, so parameters that can only have a specified set of options, you have this contextual menu where you can select, for example, the monodomain, the pseudo-bidomain, or the bidomain model to be run. And then, well, these 5 parameters are common in the whole in the 3 chambers. Then we have chamber-specific parameters, so we can unfold the left ventricle section. We can specify material ID equal to 10. And if you look at this bar at the bottom, you see also that this interface automatically provides the range of acceptable values for these parameters. Disable conduction, there's no reason to do this in the left ventricle. And ionic model, we have this context menu. We may choose Bonarovio, Pamphilov, and whatever among the choices that have been implemented. We can set conductivities for the left ventricle, and that's all. Then we go back and open the mitral valve section. Again, here we can set the material ID, exactly the same parameters. In this case, we want to disable conduction, so all other parameters are discarded in this section because no equation is solved and it is treated like an interface with normal boundary conditions on the ventricle and on the atrium side. Same for left atrium. We set the ID given by the input mesh, and we set a different unique model like the Kurt-Marshall, and that's not. So we can close now the section concerning physical constants and models, And we can set time solver parameters, output, and minimal set of applied current. Stimuli. So this one on the left is the minimal set of parameters, but having a nice user interface like this makes editing complex parameter files much more easily than the PRM data format. And this is, well, it can be shown better if we choose the full parameter file, level 2, the one that has all the parameters, including the numerical parameters. So here we have the nonlinear solver part, we can unfold and choose numerical parameters. Linear solver, we may change the solver type to GMRES for whatever reason. And for some reorthogonalization inside the GMRES and whatever. I will not go into the details of these. It depends on the level of expertise you have in numerical analysis. But having a user interface with an XML file or a JSON file makes the modification of the parameters much easier. So you can easily discard the ones that you do not wish to change. So I would like to keep default parameters for the nonlinear solver, so there's no reason for me to open this subfolder. Or I can just focus on, I don't know, the left ventricle and all the other sections with their default values. So let me show you another comparison. No, okay. Well, no, I think it's done with the XML file. I don't know if we can have. Oh yes, I think I have it here. No, okay, well, I have it in PRM format, but never mind. It doesn't matter. So with the same, exactly the same syntax, we specify the parameter file that can be even an XML file. Of course, it is supported by these two and by LifeX indirectly. And well, now I forgot to set some parameters, but the point is that you may choose as many volumes as you wish, which turns really useful when performing multi-chamber simulations. So going towards a software that is able to perform the whole integrated art simulation of all the complete models, this feature is very useful because we can use the same map for different kind of geometries. And okay, I show here example of a simulation that I run using a parameter file set up for the geometry that you see here, so the idealized geometry. Let's cut it in half so we can see better what's going on inside the volume. And no, well, okay, this is just a profitability simulation. Well, the mesh here is very coarse, so the results are quite inaccurate, but I guess you understand the idea behind this this prototype simulation, where the two geometries, the atrium and the ventricle, evolve kind of independently, and they are separated only by a layer of elements, in this case, or more layer of elements, that keeps the two chambers insulated electrically. Of course, more realistic simulations can be performed using finer meshes or more realistic meshes than this one, which is really a prototype. And also we have the calcium concentration for the different chambers. So you see, this is the calcium in the left ventricle, which comes from the Pentasher-Pamphilov model. And we also have the calcium for the left atrium, vice versa, that comes from the Ramirez-Snattel model, the two ionic models that we have set in the parameter files. Okay, and I would like to say that we have put a lot of effort into making this parameter handling more general and as flexible as possible, so that users are not needed to go deep into the code to understand how to set different models in different parts of the domain and so on. So we assign a region tag to every part of the domain. We generate the corresponding parameter file and modify it according to our needs, and simply run the simulation. Okay, so moving on, I'll just show you the mechanics model. So where we solve substantially the Cauchy equations for the displacement T, where T is the second Piola tensor with some Robin-Neumann condition on the endocardium, the epicardium, and so on. And well, actually, the electrophysiology model came with homogeneous Neumann condition, so there was really nothing to do in the assembly phase. With the mechanics model, we have the possibility to choose which kind of conditions to impose on the different boundaries. So we have the LifeX mechanics application, which share the same syntax. We have generated the default parameter file, which let me check. Okay, which by default only assumes a single volume. So, for example, a left ventricle, without changing the parameters spatially. In this part, we set the surface tags, so not the volume tags, but the tags representing the different surfaces, the endocardium, epicardium, for example, and so on. And also for other possible chambers, if we have also some atrium or descending aorta attached to this power geometry. If these are not present, all these parameters get discarded, of course. But element-based degree, okay. Here we have a set of parameters that control the boundary conditions. You can find the detail on this procedure on this paper, where we propose all the mathematical description for this the physical meaning of these boundary conditions and so on. So we have the different conditions we can set, for example, the boundary condition at the base of the ventricle in different ways. We can apply a Neumann, as you see here, declare Robin on over this special boundary condition, which is the energy consistent which has been derived with the purpose of modeling the movement of the myocardium in a more physiological way. And here, well, we have just a bit more parameters for tuning the boundary conditions. We can set the density of the material. We can choose different constitutive models for describing the hyperelastic relation between the stress and the strain. So we have the Guccioni law, the Zapfe-Logden, Neo-Hook, and so on. Here there's a typo, it should be Neo-Hook, not Hook-Neo. Sorry for this. And then again, time solver and other parameters which are all documented, but we are not interested to so far. Also, with this application, we can specify multiple volumes. The flag -1, left ventricle, mitral valve anus, left atrium. So let's just generate the minimal set of parameters and open it with the graphical interface. So here you see better the structure. Well, here we have all the boundary conditions related parameters. And as before, we have three different sections where parameters that change from one chamber to the other are duplicated. So we may set different densities on the ventricle or on the atria. If this is the case, we can choose different constitutive models for the energy functional that determines the Piaget tensor inside the formulation. Also here, so we may I don't know, set all Zapfe-Logden on the atrium just as a, I don't know, hook, Neo-Hook, and Guccioni on the ventricle. The advanced version, the more verbose version of the parameter files, we can also set the stiffness of the tissue and other more advanced settings. And well, time solver output is something that we have already seen. So as before, I'm going to present you some results on mechanical simulations. Well, one very important point that I forgot to mention is that the mechanical model can take into account for the mechanical activation of the cardiac tissue, which in terms of models, it represents the feedback from the electrophysiology to the mechanics, which is, in other terms, the response in terms of contraction or motion in general of the myocardial cells as a response to the electrical stimulus. So the electrical stimulus generates modifications in the sarcomere, other myocardial cells to activate a mechanical contraction. And this parameter can be set again in the parameter file. In particular, here we have different approaches to choose from. So we may decide to only run a passive mechanics simulation, or the approach using the active stress formulation or active strain. For the active stress, we have different consecutive models. available that have been published by Francesco Regazzoni in some of his works in the last months and years. And if running the mechanics as a standalone, we may set, for example, here. We may prescribe a given pressure on the endocardium, and we may prescribe an analytical function for the activation. This is only for testing the code and verifying the model, but this will be much more physically significant when running the fully coupled model, so the electromechanics, where the pressure and the activation comes from the feedback with the electrophysiology and the circulation model. So apart from these details, I'll show you just one example of this. Let me first open the ventricle simulation, so I can compare it later. So the mechanical model explores stresses in the domain, and in particular the displacement field. And you see that as a response to the boundary conditions and the terms that we have imposed in the formulation, the myocardium, the ventricle in this case, contracts. We can see this better if we apply this filter, work by vector, which applies the deformation to the visualization here. So we can see like this. So we can see during the heartbeat how the myocardium contracts. In this way, the analytical function only sets the pressure around in pressure, and then so this is only a contraction. There is not the diastole, just to make things clear. So just to show you again, you see the deformation, in particular here at the base, and the boundary conditions that we have implemented in LifeX are such that the apex of the ventricle actually does not move too much, which is a result that comes from physical evidence, from medical evidence. Okay. So there's also the passive mechanics simulation, same without activation. Here you see that the activation actually makes a difference in how the muscle contracts. But well, let's move to the more realistic, well, actually not that realistic, but more complex scenario of the left atrium simulation. Let's cut again the geometry. Okay. Like this. And again, work by vector. We will now see an expansion of both the ventricle and the atrium. Sorry, a contraction for the ventricle and an expansion for the atrium. This again is not physiological at all, but we have, of course, the boundary conditions to to replicate this kind of behavior, so it is expected. Okay, I think we can. Is there any question so far? The only part left is the coupling between the mechanics and the electrophysiology models that will be solved together in a coupled fashion. In particular, I have this slide that here it is, that suggests well, actually, I should have another one. Better represents the model that we are about to run. So let's focus only on the left the left ventricle and left atrium, so the left heart. We will model these two chambers in a three-dimensional framework. So we have a 3D mesh for this volume, whereas all the rest of the, in particular the systemic and the pulmonary circulation, are modeled according to a 0D circulation model. So the fully coupled. I can now go back to this slide. So the fully coupled numerical model consists of coupling the ionic model, the monodomain equation, or the electrophysiology in general, the mechanical activation, so active strain or active stress, the passive mechanics, and this 0D circulation model. We can just discard the fluid dynamics and the perfusion part. So we will focus on these first 5 blocks. And in LifeX, we have implemented different techniques to be able to save computational costs, in the sense that the electrophysiology problem requires a high level of accuracy, both in space and time, to provide an accurate solution, a numerically precise solution. Whereas the mechanical contraction and expansion actually only needs for a smaller resolution, both in time and in space. We have this kind of flexibility in our code. Okay, I now move to let me just check if I okay. The electromechanics application. Well, here is an example of the question asked by Massimiliano at the beginning of this workshop on why we need to generate these different parameter files. And well, actually, the question was another, but my answer was regarding this point. Electromechanics is a good example of coupling and on the need of generating different default parameters for different configurations. So we can have a simulation of the left ventricle with active strain, coupling with the Wien-Kessel model, or left ventricle with active stress and circulation. The underlying model, the implementation is exactly the same. What changes is what is inside this PRM file. So we have default parameters for different combinations, for biventricular geometries, and so on. So by default, when I type executable space -G, I get all of these files, because they are set up like this in the main application. And I may open, for example, active stress circulation. And here comes something interesting that I think it is better to show using the graphical interface. Okay. Correct. Let me select the correct file. Circulation. No, excellent. Okay. So the electromechanics couples the monodomain equation or the bidomain equation, or the electrophysiology in general, together with the ionic model chosen, and again with the passive and active mechanics. So just to give you a hint of what the active stress does, is a model that provides it solves some equation to provide the active tension and the active stress and the sarcomere length that describe well, the deformation of the cardiac muscle. How are these models coupled from a numerical perspective? The arrows represent the implicit coupling, whereas the orange arrows represent semi-implicit or explicit couplings. So we first saw the ionic model, then the monodomain equation, given the solution of the ionic model. Then we solve for the mechanical activation, which depends on the calcium concentration given by the ionic model, and this is done implicitly. The mechanical activation provides the active tension to the passive mechanics, which uses it to assemble the Piola tensor. And finally, passive mechanics and the circulation model are coupled together in order to let's say compute the pressure, the inner pressure that of course depend on the external circulation, and to impose volume constraints during the isovolumic phase, the isochoric phase of the heartbeat. And once you have solved these five steps, we at the next time step we use the least computed solution of the monodomain equation and of passive mechanics as an input. So it is treated explicitly for the ionic model and the mechanical activation, and the mechanical deformation for the electrophysiology again. And well, so I will show you first one example of running all of these models on the same mesh, and another example using two different meshes for the electrophysiology part and the mechanical part. So, since there are many physics involved in the electromechanical model, the parameter file contains different subsections. Well, fiber generation, we know what it means. Electromechanics just contains a set of minimal parameters for that are common among the different physics, such as the mesh, the time solver, the time span of the simulation, and the output. So we have no physical parameters inside the electromechanics model. Then we have two sections, active stress or active strain, each one with its own physical constant and models, and the one or the other is read depending on what we have set up in the mechanics part. So if here I set active stress as an activation model, then the active strain section will be discarded. So you see that the parameter files coming from the mechanics standalone, the electrophysiology standalone, and the activation as standalone are just glued together and nested in an organized way, so that we can control easily everything concerning both the overall the big picture of the simulation and also the low-level details of every model. And in particular, since from a numerical point of view, the two models are quite a lot different to solve in terms of spectral properties, convergence, and so on, we may also set different solvers for the electrophysiology and the mechanics, for example. So I just move on to show you some results that again will not be okay. So first type of simulation is well, as usual, the idealized ventricle geometry. And on the same output file, we have the solution to all the models that are coupled together. So we have the calcium concentration, the activation variables, the displacement provided by the mechanics, the mechanical model, and the transmembrane potential. So let's assume to deform the mesh according to the displacement provided by the mechanics, whereas in the plot we will see the transmembrane potential. Well, sorry, the animation is a bit slow. We have I have many time steps. It's a bit faster, but you see what happens. So the domain contracts, deforms, and the deformation is also affected by the solution to the ionic and electrophysiology model that provide a feedback to the activation. I'll show you again. Chapter. Sorry for these interruptions, but doing things like always requires a bit of tuning. And in this case, everything is solved on this, well, of course, but it is a unique mesh. The same that we have used before for simulating the electrophysiology and the mechanics problems as a standalone. We may also implement this strategy where we use a fine mesh for the electrophysiology part and the coarse mesh for the mechanical activation. We have it here. Now I have two files because the mesh is different, so they need to be loaded separately. So here on the left, you see the well, I opened twice the same file. So we have the electrophysiology solution on the left and the mechanics problem solution on the right. We can, as usual, let's just work with Pasquale vector and plot well, let's do it like this. And you will see that the two simulations, of course, are synchronized, but the electrophysiology mesh is finer and the coarse mesh is coarse by definition. So you see that the geometry is the same, but the electrophysiology mesh has been obtained by refining the original one. Okay, so let me remove these lines and let's try to run the simulation again. 50 frames should be enough. See that even if it is a very idealized prototype, and even if both meshes actually are not that accurate for a physiological simulation, we get a physiological behavior. So the left ventricle activates different points, which then influence the activation model, which is included in the mechanical model to drive the deformation. Okay, final simulation that I would like to show you is a single mesh simulation on the left part. So this is the as before the electromechanics, but now we are setting different models in the ventricle and in the atrium. And the different models are both for the mechanics and both for the electrophysiology. So I should have a slide here. So consider only the right part of the screen, so the left part. We set actually different passive mechanics models. The mitral valve, the purple one, is electrically insulated, and we set the pentasher model in the ventricle. And so, in principle, all of the three different physics, which are electrophysiology, mechanics, and activation, can be set using different constitutive relations or models in each of the three chambers. But this also holds for the whole heart simulation that we are going to perform in the next month. Okay. So as before, in this specific case, just as an example, we disabled the conduction in the atrium and on the mitral valve, just to test the implementation of this kind of multi-volume handling. And well, actually, I didn't show you the deformation. So it was only part of the solution. So we start from this configuration. It deforms in this time in not a very physiological way, but well, the parameters are completely out of tune. That's not the point. And both solutions are stored in the same mesh. And we can simulate different heartbeats. You see that starting from time step 80, a new stimulus applied current is set. So we have one heartbeat and something more, the initial phase of the second heartbeat. So, well, I think it concludes all the prototype models that I wanted to show you, and the capabilities of LifeX of performing complex simulations by keeping the implementation as simple as possible, and also giving the flexibility of choosing different coupling schemes. What I didn't say actually, perhaps I mentioned it, but it is worth repeating it again. The models that we have implemented actually are many more than the ones that we have seen today. We have also model for myocardial perfusion, for dynamics and valve dynamics. We have simulations on the two ventricles or on the whole heart, as the one that I have just shown you. The pulmonary and systemic circulation. We have the aconal model for the electrophysiology. We have coupling between the electrophysiology problem and the torso electrical diffusion. So we can solve an interface problem where we replicate the simulation of an electrocardiogram. We have also with structural interaction coupled with the electrophysiology and activation. So this is the most complex model in terms of how many models are coupled together, and also in terms of how the two geometries are dealt with. And well, I think that's all from my side. I would leave the next minutes for questions, for curiosities, and I remind you that by the end of this year, LifeX will be open, will be released open source, and you will be free to use it to contribute it eventually. Well, the documentation is something that we are putting a lot of effort into. So we have very detailed instruction on the download, installation, but also the single models, as you can see here, are described with their numerical formulation, so time discretization, space linearization, and so on. So we'll try to keep everything as transparent as we can. And I thank you for your attention. Let me see. If you have any question, just unmute yourself or raise your hand. Okay, so
your last words. Do you think that the session is concluded, or?
There is a chat message, a question in the chat, so I'm going to
Okay, sorry. No, go ahead.
Okay, so the question is, how can we implement a new constitutive model for the mechanics? For the mechanics model. I will show you everything is implemented here. Sorry, can you hear me?
Yes, we can hear you. You've been frozen just a few seconds. Now we see you, but we don't see your screen.
The client just closed the...
We don't see your screen. Okay, now we see your screen.
So I was saying, let's take, for example, the hook energy functional, so I can we can compare the. well, let's see a more complicated one. The Puccioni law always has this problem. So yeah, this table at the moment to do the shoot. But, however, the implementation is a simple C++ class where you define model parameters. So the Puccioni model depends on these parameters PF, PS, PN. You set the default value for them and the description, possibly. These are the ones that will be printed to the parameter file. This is the part that instead reads from the parameter file and sets variables in the class. And then you have a compute W that implements the computation of the total energy given by the Puccioni model, taking as an input the deformation tensor. And inside this function, you may implement your constitutive relation very easily and return it. Here we even have a volume constraint. So, and also these two provide many facilities for dealing with tensors and computing scalar product. As you see, it is very extensive. The determinant, we can compute the tensor E very easily, and also compute the sum of different tensors, but multiplied by coefficients. So this is for the energy part, and then you just implement its derivative with respect to f, which is the Piola tensor, in the same way. So you compute the derivative and implement it here. So in this case, for Puccioni, the Piola tensor has this expression that even if someone does not know C++, I guess they should be familiar with what we find in a classical paper written. I don't know if this, okay. Thank you, you're welcome. Question, how can you incorporate CT scan or MRI data in your code? Well, actually, there are many different ways, many different types of data that we can import. Some of them concern the pre-processing phase. Just like in this example, you take from a cine MRI the motion of the left heart, for example, and you convert it, you translate it to become a computational mesh. This example is outside LifeX because everything that is pre-processing the mesh or post-processing the result is usually outside LifeX. But we have tools that have been developed by Marco Fedele, one of the other collaborators in the IARC group, in particular in the VMTK library, that also interfaces with MITK, if I'm not wrong. It is able to perform the segmentation of images to build a surface that we can build a computational mesh on. Another kind of application is importing data that are defined on a mesh that you already have at your disposal. Like in this figure, you see that we have a section of a left ventricle, and these red and gray zones represent necrotic tissue, so ischemic regions and the gray zones. This datum has been provided by by clinicians. They have determined it according to their imaging, and this data can be directly interpolated into for example, a finite element vector in LifeX, or be used for tuning, for importing coefficients from file, or something like this. I don't know if you have any more specific question. I would be glad to answer. This is just a general overview. And also on this slide, we see another application on how to reconstruct the volume motion from imaging data. Okay, thank you. You're welcome. Okay, any other question or curiosities, or even just comments? Everything that.
Just a very, very quick curiosity.
Yeah.
When you run high order, can you save to file the high order cells? Like, can you export a solution as a P2 solution and then read it in ParaView as a P2 solution?
Well, that's another good point. I think, if I'm not wrong, I mean, I'm not really expert on this, but if I'm not wrong, the most common data format, such as BTK, BTU, and so on, do not support exporting of higher order polynomials. What we can do, and is actually done in this tool and we use in LifeX, is to divide every cell into sub patches. So if you have, for example, degree 2, you take the cell, you assign the values, you refine it, you assign the values taken from the quadratic solution, for example, and in the post-processing phase, they will be seen as a linear solution, but on the smaller sized cells. I don't know if this is clear.
Yes, it is clear. I'm asking because, well, I'm asking all questions about stuff that my code doesn't have. And I looked into this some time ago, and it looks like VTK has a sort of specification for higher.
There's a reply in the chat by Peter, which is one of the authors and main developers of these two.
Ah, good.
And
thank you, Peter.
well, I was not aware of this plan, so it is possible.
Okay. Well, very good. Thank you very much.
You're welcome. Thank you, Peter, for the hint.